Okay, so let's consider our equation for our straight line again. So we had r of t equals some vector a plus u times t. Okay, so what we had drawn was we have some origin O. We go some vector a. And then at this point we add the vector u times t, which takes us along this line, which is in the direction in which u points. So ut will take us to this point. Okay, and this r is a plus ut. It's this vector here, r of t. Okay, and it's defined by t being any real number. Okay, so when t is 0, as we said, r is just equal to a, so we're at this point. So this is t equals 0. If t is greater than 0, we move in this direction. Okay, so the point lies along this part. If t is less than 0, then the point will lie along this part of the line. Okay, but as you change t, you map out this straight line. Okay, so we drew this in kind of 2 dimensions, where we're thinking about a 2-dimensional coordinate system, x and y. And of course you know that this has unit vectors I hat and j hat. Okay, so you can have r equals, so if we have some vector r, this can be written in terms of the components. Okay, so we have x along the I direction and y along the unit vector j. All right, but this form of the equation that you see here, this is a vector equation, okay? And this applies equally well in 1 dimension, 2 dimensions, or 3 dimensions. Okay, so this is the 2-dimensional case. If we think about the 3-dimensional case, this still describes the equation of a line. Okay, so what we're saying is that in this case we have r, which represents some coordinate x, y, equals a, and the components of a are ax and ay, plus u, and the components of u are ux and uy, times t. Okay, but if we move to 3 dimensions, and let me draw a 3-dimensional coordinate system. Let's have x, y, and z. Okay, then we've got unit vectors I, j, and k. Okay, they're our basis vectors. And our vector r, which is at now x, y, z, has 3 components. It has an x component, a y component, and a z component, and you can get this by just resolving along each axis. So in 3 dimensions, this just extends to x, y, z, and then we need 3 components for this vector a and 3 components for the vector u. Okay, so we're going to be thinking in general about 3D curves too, that depend on some parameter t, and they're going to be parameterized by x of t along this direction plus y of t along the y direction plus z of t along the z direction. Okay, let's think of an example. let's think about a helix. Okay, so here's our helix. This is our three-dimensional coordinate system, x, y, and z. Okay, and our helix is defined as follows. It has x equals a cosine t. Y equals a sine t. Okay, and if this, as we've seen before, these describe the equations of a circle of radius a. Okay, so if we were just to stop here, as we changed, and let's have t going from 0 to 2 pi. Okay, if we were to stop here, this would just map out a circle in the xy plane of radius a. Okay, but that's not a helix. What happens in the helix is, as you go around the circle, you also lift out of the plane, so you get higher in z. So as time goes on, z increases, and let's let it increase linearly with t. So this is a constant called b. Okay, so what happens is you start here, t equals 0, which has x equal to a cosine t, which is just a, and y equals a sine t, which is 0. Okay, so this is the point a, 0, 0. That's where you start at t equals 0. Okay, and then t increases and you rotate anti-clockwise around the axis, but this bt term takes you up higher. So as you go around, you lift. Okay, and there should be a fixed radius of radius a at all times. Okay, so this is a helix. This is a three-dimensional curve. Okay, and it's important to be able to describe curves like this. Of course, if you want to describe DNA, this is a helix, or the thread on a screw. Okay, so if you're manufacturing something, or you're studying some properties of DNA interactions, or modeling them quantum mechanically, you need to know about the structures involved. Okay, so you need to be able to calculate lengths and positions of molecules, etc. So it's important to be able to do this. Okay, one more example. So let's now look at one final example, and let's think about the motion of a projectile. Okay, so let's think about, here's the surface, and some projectile is projected from the origin, O, at time t equals 0. Okay, so at t equals 0, projectile is launched. Okay, so maybe I threw this pen, so I let go at t equals 0. Okay, and the position at which I let go, that's the origin of our coordinate system. Okay, so let's call this the x-axis, and let's call this the z-axis. Okay, so we're thinking about projectile motion in the xz plane. The y-axis points towards you. Okay, but we're not going to consider motion in the y direction. So let's say that this projectile is launched with some angle alpha, with some initial velocity v0. Okay, so t equals 0, the projectile is launched with velocity v0. Okay, so we know what this angle is, alpha, so we know what the components of v0 are. It's v0 cosine alpha in the x component, the y component is 0, and the z component is v0 sine alpha. Okay, so if I throw this pen up, it won't just keep going up. Okay, gravity, the whole earth is pulling down on this pen. So the pen will fall. Okay, so we have gravity acting. Okay, an acceleration called g. It's a vector. It's a vector straight downwards. Okay, so we can write it like this vector, but it has components 0, 0, minus g. Okay, where g is a number. So this is 9.81 meters per second. Okay, and the minus tells us that it points downwards. All right, okay, so if we have this type of setup of a projectile, then you'll know from your mechanics that the coordinate r of t is given by v0 times t. Okay, so distance is speed times time. So this is the projected velocity, v0 times time. Okay, but there's also gravity acting. So we get a plus g vector t squared over 2. Okay, so this is a vector equation. All right, so this is the vector equation for the projectile. All right, and we want to think about what the x, the y, and the z are in this case, and that's all. Okay, so this is just, we can write this in component form. So we can write r of t as x, y, z. Okay, and v0 we know is v0 cosine alpha. Y, the y component is 0, and the z component is v0 sine alpha. So that's this first term, v0 times t. So let's just put the t's in here. Well, let's put it here. T plus, and then gt squared over 2. Okay, so we've got 1/2. G is 0, 0 minus g. 0, 0 minus g, and we've got a t squared. All right, so the x component, this tells us that our x of t, okay, this thing, is equal to v0 t cosine alpha plus 0. Okay, so that's x of t. Our y of t is equal to 0 plus 0. Okay, and our z of t equals v0 t sine of the angle. Now we've got plus and minus, so this is minus g t squared over 2. Okay, so that's it. Okay, so these equations parameterize our projectile. Okay, we can think about, this is maybe just a little bit off the board. So this is gt squared over 2. Okay, we can think about what kind of curve this is. All right, so we've got x equals v0 t cosine alpha, and z equals v0 t sine alpha minus gt squared over 2. Okay, so let's think about what type of curve this is. So the first equation, 1 and 2. So 1 tells us that t is equal to x divided by v0 cosine alpha. Okay, so at any position along the projectile motion, at any x, y, z, at any time, this will be true. So we can substitute this into the second equation. Okay, this tells us that z equals v0, t is x over v0 cosine alpha, and we've got a sine alpha here. minus gt squared over 2, so we've got a g over 2, and t squared is x squared over v0 squared cosine alpha squared. So the v0's cancel. Sine alpha over cosine alpha is tan alpha, so we've got x tan alpha minus g x squared over 2 v0 squared cosine squared alpha. Okay, so in terms of a function, we've got z equals some function of x, and that function of x has 1 power of x here and 2 powers of x here. Okay, and it's got a minus sign in front of the x squared. Okay, so this motion is a parabola, as you know from your mechanics. Okay, so hopefully that was familiar and a bit of recap for you, and helpful recap at that. Okay, we're going to move on now to think about curves more generally in space and how we can describe them